Here we have an equation 2x1 plus 3x2 equals 6. Now we might be more used to saying the same equation as 2x plus 3y equals 6. We don't want to use different letters for all the variables because in linear algebra, we can get a whole bunch of variables. We do better if we subscript variables, but we can understand that x1 is like your x coordinate, x2 is your y coordinate. And if we went to an x3, we could use that for a z coordinate. If we have 4 variables or more, we can't visualize it anyhow, so it doesn't really matter if we call it x1, x2, x3, x4, or x, y, z, w, or whatever. We can't really sketch it, and we just have to do everything formally. And for the most part, at least in the early stages, guided by our intuition, what happens in 2 and 3 dimensions. Okay, so this is simple linear equation in 2 dimensions. In 2 variables, it's going to be graphed in 2 dimensions. And it's very easy to graph this equation. Just let x equal 0, you get y equals 6 over 3, which is 2. So you have the point 0, 2. That's your y-intercept. So let's right there is your point 0, 2. And let y equal 0, you get your x-intercept, and you get x equals 6 over 2, which is 3. Okay, so this point goes here, this point goes here. And I'm not going to go into detail on how you graph these things. We're just graphing linear equations. And if you're not expert at graphing linear equations, you need to become expert very quickly. If at this stage you're not expert at that, and then there's something deficient in the courses you've taken, or maybe you were just deficient that week. Okay. But it's real easy to remedy, real easy to do these. So it's not beyond anybody's ability to understand how to graph linear equations in all aspects within just 30 minutes by the time you're at the level of this course. Okay, so fix that if you don't know how to do it. Okay, now associated with this linear equation is what we call a homogeneous equation. Of course, this is part of a review halfway through a linear algebra course, and we know what homogeneous equations are. Instead of having this thing equal to 6, we just have 0 here. In other words, you have a multiple of one variable, a multiple of the other, and no other numbers. Okay, so that when you write it as an equation, you're going to end up with an equation in this form, or an equation you can put in this form. Okay, well, that's a graph. The graph of this equation is graphed through the origin with a slope of -2/3. Obviously, it goes through the origin because the only way 2x plus 3y is going to be 0 if x and y are both 0. And if you solve, put this in slope-intercept form, y equals 3y is going to equal -2x, so y is going to equal -2/3 x. It's going to have a slope of -2/3. And you can graph that easily. So we can graph that, okay? We go through the origin. And if we go over 3 units, if the run is 3, the rise is going to be -2. So we move over 3 units here. That 3 didn't come out very well, but and down 2 units here, it puts us at the point 3, -2. And the graph goes through these points. And of course, both of these equations have identical slopes, so they're parallel. Didn't do a good job of drawing it that way, but they're parallel. Okay. So the equation in the homogeneous version I say are parallel. The graphs of those equations are parallel, but I'm not going to correct that. Okay. Now coming over here, in the notation that we want to expand, if we want to go to 3 equations and 1, 2, or 3 unknowns or whatever, we write the same equation, but using x1 and x2. Our solution set is infinite. In other words, for any value of x1, the value of x2 is determined, but x1 could be any real number at all. and you would get a value of x2. And when you run through all the real numbers, let's just say you did this for all real numbers x1. Now, that would take a while because there's an uncountably infinite number of such numbers. But let's say you did that and plotted all those points, you would have this line. Similarly, you could let x2 take any value, okay? And let x2 take all possible values of real numbers, and each value of x2 is going to imply a value of x1. And when you do all that, you're going to get the same line. Okay, when we, let's say, let x2 vary over all real numbers, then we're going to call x2 a free variable. And we're going to, for reasons that'll become apparent, we're going to say, okay, we'll say let x2 be the free variable. I'm going to represent the values of x2 by the parameter p, t, by the parameter t. So if x2 equals t, well, then 2x1 plus 3x2 equals 6 becomes two x1 plus 3t equals 6. So that, and do arithmetic, subtract 3t from both sides, divide by 2, you get x1 equals 6 minus 3t divided by 2. Quantity 6 minus 3t divided by 2. Or x1 equals 3 minus 3/2 t. Okay, now we express the solution in linear algebra. We want to express it as a vector. So x1, x2 equals 3 minus 3/2 t, that's what x1 is. And x2 is t. Well, that's pretty good. I can then pull this expression apart. Sort of factoring it, although we're not really factoring. Kind of feels that way, but we're not dealing with multiplications. You can verify that this adds up to this. Now, the way I looked at it is just, well, the number we have here, the unaccompanied number is 3. And so if we want to write this as a sum of 2 vectors and separate out that 3, well, we're going to have a 3, 0 here. We're going to have 2 coordinates, and we don't have a number that goes with a t. So we're going to have a 0 here. And then we have negative 3/2 t. And if we just factor the t out, there we have it. Okay. Well, that has the advantage of telling us that the graph of this function, or the graph of the solution, depending on the value of t, Where'd my blue chalk go? I'm getting down to the end of this blue chalk. Okay. I take the vector 3, 0, which is fixed. Now in the plane, that means I'm going to use, let's say, yellow for the vector 3, 0. Okay, so here's the vector. Figure out where to draw this, and there's no good place. Write it pretty small. So here's the vector 3, 0. Now we identify this vector with the point at its tip. And then the vector -3/2, 1. Well, we come over 1.5 units, half of 3 units. That would be about this far. And then up 1 unit, and we have a vector that maybe looks like this. So here's the vector. -3/2, 1. Excuse me. Now, if we multiply this vector by t, if t is a positive number bigger than 1, then we're going to get a vector in the same direction, rooted at the origin, as is always the case when we represent vector spaces in R2 and R3. It's going to become longer. Okay, well, depending on the value of t, we get any vector in the direction of this -3/2, 1 vector. And those vectors could end up anywhere on this more or less straight line. And if t is a positive number less than 1, of course, we can end up with numbers that would end up with vectors shorter than this vector. So we end up with numbers here. And then if we use negative numbers, we can end up with vectors that end anywhere along this line. So any vector that starts at the origin and ends on this line is a multiple of -3/2, 1. Okay, now I want to make sure this blue vector is prominent because it's an important aspect of what we're looking at. Okay. Well, that's kind of interesting. If we add 3, 0 to one of these vectors, well, that means we just take an arrow this long in the horizontal direction and add it to any vector that starts at the origin, ends anywhere on this orange line. And it should be pretty clear that that's going to give us a set of points that all lie 3 units to the right of this line, that all those points are going to lie on a straight line. I don't think it's going to work out that way, the way I drew these, but let's just see. Yeah, not too bad. Kind of went through my 3, 0, but I knew that was going to happen. So what we end up with is a line parallel to this line displaced by this vector. Here's the key now. Any point on this line is a solution, represents a solution. This line represents all solutions of our equation. this line represents all solutions of the homogeneous equation. Now, I didn't leave myself room to write that anywhere. Solutions of homogenized equations, homogeneous equation lie on this line. And of course, now, if you look back at this picture, we already knew that. Okay, so just to finish the color coding, this vector is here. T times this vector is going to give us vectors that end at points on this line, and every such vector will be of this form. And when we add these two, we get the set of all solutions. And of course, because of what we did here, this does represent the set of all solutions. So this is a big deal. And I did leave myself room for a statement over here. Okay, so this is kind of a pretty big deal. In vector notation, every solution has the form V equals I'll use H, V sub H for homogeneous. The vector that solves a homogeneous equation, that would be this, one of these, okay? And those are the vectors whose ends lie on this line. I'll kind of underline that in orange. And then plus we're going to call this VP. And I'll give you a little explanation on that. Okay, this VP, what we call a particular solution. And VP could be any solution of this equation. So this is any solution of the equation. This is a solution of the homogeneous equation. And I hope the video comes out clear enough that we can see this. One solution of this equation is 3, 0. That's the one that we used here. There are other solutions. For example, 0, 2. Okay, 0, 2 is a solution. So solutions of this equation are not confined to the solution that we used here, but you can see that if we add 0, 2 to the point that goes through the origin, right there's the vector 0, 2, and it takes us to this red line. Okay, we could have the vector, let x1 equal 1, then x2 is going to have to equal 4/3. So we could take the vector 1 unit this way, 4/3 unit this way. We would again end on the red line. So any solution of this equation gives us a vector, which when added to the vector that ends on this orange line, lands on the red line. Okay. So this is the beginning of a kind of a really big deal, really important aspect of matrices and linear transformations. Simple one-dimensional case. So you really want to understand this because I'm going to go on and look at higher dimensional cases. Just to try to make these points really clear, bigger picture. Again, we have this equation. Its solutions we've seen have this form, where t can be any number from -infinity to infinity. And it has these solutions and no other solutions, meaning all the solutions lie on a line. It's parallel to the line t times -3/2 1. This line here that we've seen. Here's your vector -3/2 1. And vectors that are multiples of this vector all lie on this line. And every vector that has a tip that lies on this line is of this form. So here's your set of solutions to what we call the homogeneous equation. Okay, the homogeneous equation is equation 2x1 plus 3x2 equals 0. And we've seen that that is the solutions of that equation are represented by a line through the origin with a slope of -3/2, this line parallel to this. Okay, so we've established that. The solutions to this equation then can be all constructed by first constructing this line, a set of solutions to the homogeneous equation, and then displacing every point on this line with a vector 3, 0. Okay. For example, displaced by the vector 3, 0 here, we get to this point. Okay. Now these lines are supposed to be parallel, and we've seen why. And didn't quite get that exactly right when I sketched it, but for a freehand sketch, these indicate parallel lines. So if they are parallel, then the vector that goes from here to here would have to be the same as the vector here. Okay, well, how is that a sum of this and this? Well, your this vector here is a multiple of this vector. It looks like it's about 2.2 times as long. So be -2.2 times this vector, get you to this point, and then this vector gets you to this point, and this point represents a solution. Estimate the coordinates, you get an estimated solution, but the coordinates of this point plugged in here solve this equation. So one way to see the construction of this line by this breakdown is like so. We just displace every point on the homogeneous solution, the line representing the solution of the homogeneous equation, to this particular solution, 3, 0. This illustrates part of my statement that every solution has the form V equals VH plus VP. Okay. VP is any solution of this equation. So if we want solution represented by this point, there is some solution of the homogeneous equation that gets us there by this vector, namely, move 3 units to the left, and right there it is. So here's a solution to the homogeneous equation, whatever the coordinates of this point are. Just place 3 units to the right. In other words, add 3 to the x1 coordinate. You get a solution to this equation. Okay, now I say that this could be any solution of this equation. So there's no reason that I couldn't looking for a piece of chalk. Got to pause for a second. Well, it looks like I'm out of colors. Don't like to use green. At the same time, I'm using yellow because they kind of almost look the same. But it's going, okay, now there's no reason I couldn't get to this point from any point I would choose on this line. Okay, so for example, if I want to get to this point from here, right here is a vector. Now, in this case, I would have a vector VH that goes from here to here. Okay, so I have a vector from the origin out to here. So here's my vector VH, and I'm going to draw this a little more clearly in a minute. And then here's my vector VP. Now I said I'm going to draw it a little more clearly because that is probably about as clear as mud. So here's a set of homogeneous solutions. Here's a set of solutions of the equation. And let's just say we've got our origin at some point here. So I'll just draw a small x and y axis to indicate where the origin is, so that I can indicate where this vector -3/1 is, the vector that we're really kind of, well, the vector we use to get the set of homogeneous solutions. Okay, so if I'm looking to get a solution here, whatever the coordinates of this point are, they're going to be a solution to this equation. Then I can get to this point from a whole variety of points, okay? And kind of analogous to what I drew there, I could get there with this vector. This would be a VP a particular solution. Okay, well, what particular solution? Well, maybe this is 1 unit and this is 4/3. Okay, so the x coordinate's 1, y coordinate's 4/3. Well, if x is 1 and or x2 4/3, x1 and x2 1 and 4/3, it gives a solution. Because that gives us 2 here, and 4/3 of 3 is 4. 2 and 4 makes 6. So this could be a different particular solution. In other words, this 3,0 doesn't have to be 3,0. It could be any vector at all. And of course, then we have our there it is. We have a vector here that's BH a homogeneous solution. What I say is then, if I want to get this solution, I can use any solution of this equation. And if that solution is 1/4, then I can find the vector here that gets me there. Okay, well, that illustrates it. And the other upshot of that is that any vector gets me from a point on the homogeneous solution, a vector for the homogeneous solution to the solution space, the set of solutions here, is a solution to this equation. Now you might chew on that a little bit, but we're going to look at this in higher dimensions. Okay, now let's take system of two equations in x1, x2, and x3. So this is, each of these equations is going to represent a plane in 3 dimensions. And when you intersect 2 different planes in 3 dimensions, unless the planes are parallel, you're going to get a line of intersection. Okay, so these 2 planes are not parallel. We would get a line of intersection in 3 dimensions. And we're going to talk about that a little bit. But first, let's just reduce these equations. Okay, now I've got an error in here someplace because I've got a result over here that solves one equation, doesn't solve the other, although it's kind of reasonably close almost. And I'm not going to take the time to fix that because it doesn't really matter for the picture that we're going to get. But of course, you want to solve the equations correctly if you want everything to come out just right. And we typically want that, don't we? Okay, so I'm not going to worry about that. I've looked at it twice and somehow I'm stuck and there's something wrong, but it's pretty straightforward. Reduce this, we take half of the first equation, we get 2, 1, 3/2, 2, 6. Right there we have it. Okay, and then we add 4 times this equation to this equation. And I think I see where I went wrong. Yep. Something's haywire in my brain here, but that's okay. Okay, so I might correct this and I might not. Okay, so I take 4 times this equation and add to this equation. I'm going to get 0 here. And 4 times 3/2 is 6. I don't get what I've got at all. I'm going to fix this, come back in a minute. Okay, I hope I've got it right. Okay, again, take half of this when you get this, then add 4 times this to this. 4 times 3/2 is 6, 6 and 6 is 12. 4 times 2 is 8, 8 and -3 is 5. And 4 times 6 is 24, add that to 48, you get 72. My problem before is I keep looking at the wrong equation. Eyes aren't working right. Okay, so anyhow, we then take 1/12 of this equation, we get this, it's very straightforward. And then we take 3/2 of this equation, or -3/2 of this equation, and add to this one. Well, -3/2 of 6 is -9, -9 and 6 is -3. -3/2 of 5/12 is 5/8. Work that out. Maybe I'm wrong. And you subtract 5/8 from 2, which is 16/8. 16 minus 5 being 11, you get 11/8. So I kind of think this might be true, but if it's not, easy to fix, and it's not going to affect what we see as a result of this analysis. Okay, now we see that we only have two equations. We have three variables, so we're going to have one free variable. We're going to let x3 be the free variable. So for any number, in other words, we want to choose for x3, we get a value for x1, and down here we get a value for x2. Okay, so let x3 be free, and let x3 be our parameter t. Then this equation becomes x1 equals -3 minus 11/8 of x3, but that's not going to be 11/8 t. And this one becomes x2 equals 6 minus 5/12 x3, or 5/12 t. Okay. And so we can say then that our vector x1, x2, x3, representing our solution, is -3 minus 11/8 t, 6 minus 5/12 t, and x3, which is just t. And this equals the vector -3, 6, 0 plus t times the vector -11/8, -5/12, 1. Now, fractions over here are kind of a pain. We can represent exactly the same set of vectors if we just say, okay, we're going to let t be 1/24 is great, essentially. And not all that important to understand that, but if I multiply all of these numbers by 24, I get -33, -10, 24. And that's legal because any multiple of this, well, this is a multiple of this. So any multiple of this by any t can be expressed by multiplying this by just a different t. In other words, the set of all multiples of this vector is the same as the set of all multiples of this vector. Now, the t here is going to be different than the t here, but we just let t absorb that constant that we multiply by this vector the same way you do in integration, where you let your arbitrary integration constant absorb whatever operation you're doing. So we have this representation of the solutions of this equation. And we can graph that representation in three-dimensional space. Okay, I don't have a lot of room to graph it, and I want to do a bigger graph, so I'm going to do that. But you can say, okay, here's three-dimensional space. x1 this way, x2 this way, x3 this way. This vector is -3 on the x1 axis and 6 on the x2 axis. So it's, let's say, out here someplace. And so that's kind of, the board's a little rough there. But you got this vector that represents this fixed vector. You've got this vector, -33, -10, 24. That's a much bigger vector. It's 33 that way, 10 that way, and 24 this way. So it's going to be a vector that will at least be parallel to a vector that goes about 3 times as far this way as it goes this way, and about 2/3 as far this way. So it's kind of like that vector would be represented by a diagonal of a box It might look something like this. And I'm not assuming that you know a lot about graphing in 3 dimensions. So I'll explain this a little more when I do it. But then this is going to give us, well, this is a solution to the homogeneous equation. That's going to give us our line here. And the line goes through the origin in this back corner of this box. And then we have this particular solution that will displace any point on this line. And I haven't drawn that well at all, but you get the idea. To give us the solutions to this equation. So we're going to draw that out and make it bigger, but I wanted to give you a quick picture and show you that all we're doing is the same thing we did before. Okay, we have, oh, sorry, messed that up. But we have this, our solution to the homogeneous equation, and our vector here, and color coding in a similar way to what we did before. Now we'll pick that up on a different board and try to make sense of it. Okay, to summarize, we had a system that could be represented by this augmented matrix. I want to write out all the x1s, x2s, and x3s. We understand augmented matrices. This matrix, if I did it correctly, reduces to this one. And this matrix gives us the equation x1 plus 11x x3 equals -3, x2 plus 5/12 x3 equals 6. And we then just put the solution x1, x2, x3 into this form, where x3 is a free variable represented by t, so that x3 is equal to t. And we separate the solution out as we did previously, and we separated solution out into this. We multiplied the actual column that we got here by 24 to eliminate denominators. So we have this representation. Now, let's look at this vector. And I'll tell you why I did this in a minute, but let's look at this vector. This vector is -3, 6, 0. Now here I've drawn an x1, x2, x3 set of axes. This vector -3, 6, 0 means that we have a point whose coordinates are -3, x1 coordinate is -3. Now these little marks I've drawn here on the axes are just unit marks. Here's 1, here's -1 on the x2 axis. Here's 1, -1 on the x1 axis. Here's -1 and 1 on the x3 axis. So if I want to get -3, 6, 0, I've got to go 3 units back, negative x1 direction. So that puts me here at this point. Now, let's kind of make that yellow, because I'm using yellow for this particular solution to the equation. Remember what that means. And if you don't remember, that's okay. It'll take you a little while to sort this out. Okay, so here's 6 on the x2 axis. So our x2 coordinate is going to be 6. And our x3 coordinate is 0. So we just then go to the point -3, 6 in the x1, x2 plane. We don't have to go up or down because our x3 coordinate is 0. And we locate this point and we draw a vector. And we can see where this vector is. It's flat, meaning it's in the x1, x2 plane, and it goes back in that direction. Okay, well, that was fairly easy. Now this is going to be a particular solution. This is the particular solution we use to model this situation. So this is going to be our I said YP, it's a V. And I didn't leave myself room to put an arrow over the V. So let's just fix that. Okay, so we have VP, a particular solution. Okay. This solution, x1 equal -3, x2 equals 6, satisfies both equations, I hope. Let me look back at the equation. Let's see. I mean, I could look at this. -3 times 2 is -6. 6 times 3 is 12. 6 times 3 is 18. And -6 is 18 gives you 12. Okay, that's good. -3 times -4 is 12. 6 times 6 is 36. 12 and 36 is 48. You go back to the original equations and see that this works. Okay, so this is a solution to the system, which makes me suspect maybe I did something right. Okay. Okay, again, there's our particular solution. A specific solution to the system. Could be any solution, but this is the one we got, the way we chose to solve the equation. Now we have this vector. And this vector has big numbers. I don't have room on the board to do this vector. So as I did before, when I multiplied the vector that we actually got by 24, I multiplied all the components by 24. I'm going to divide them all by 10. Okay, and now I've got this. And this is equally valid because all the vectors we get when we multiply t by this, the same set of vectors we get when we multiply every possible t by this. Okay, it gives us the same line. Okay, so this vector is manageable. I can draw this vector up here. So to construct that vector, so you can see where it is, I got to go -3.3 in the x direction. That's going to put us x1 direction. Going to put us a little over -3. -1 in the x2 direction. That's going to put us here. Now at this point, if this was all there was to it, we'd have a vector from here to here in the plane. But it's not in the plane because we have a 2.4 coordinate in the x3 direction. So here's 1 in the x3 direction. Here's 2, and here's 3, and 2.4 is going to be about here. Okay, now to see where this vector is, first of all, we're going to draw a rectangular solid, a rectangular parallelepiped, if you want to use the terminology. So we're going to have one side of this box, think of it as a box, along here, another side here, parallel to this side, through this vertex. Now, this point, this point, this point, and this point are all vertices. This point is a vertex, this point is a vertex. We're going to have one back here and another one back here. Okay, the height of this box is our 2.4. Here's a quarter, here's a quarter. We've got to come up 2.4 here. So we've got to draw a segment that's the same length as this one here. And another one here. Now we got the 4 corners of our box. Well, we got 4 corners down here, and we got 4 corners up here. All we've got to do is join them. Now the dotted line I draw here has to be parallel to the x1 axis because this edge of the box is along the x1 axis. This side has to be parallel to the x2 axis. There it is. This one also has to be parallel to this one or this one or this one, parallel to the x2 axis. So there we have a box, okay? And I'll even make some of these lines solid and keep some of them hidden just to show you as well as possible where this box is. Now this vector rooted at the origin goes to this far corner of the box where the coordinates are -3.3, -1.0, okay, and 2.4. So here's the point. And here's our vector. This is the vector -3.3, -1.0, 2.4. If I multiply, get the right color here, I multiply this vector by all possible real numbers t, as we saw before, I get a line. And this picture is just the same as a picture it was when we had an equation in 2 variables and everything was in the plane. It's just that now everything is in 3-dimensional space. So we get a line here. Okay. This line is a set of solutions to the homogeneous equation. So there they are. Now let's write out the homogeneous system just to make sure we understand the connection. The original system was 2x1 plus 3x2 plus 4x3, and it was equal to 12. Well, in the homogeneous system, it's going to be 0 because that's what a homogeneous system is. A homogeneous system doesn't have any numbers floating around except for the coefficients of your variables. And then we're going to have -4x1 plus x(2) minus 3x3 equals 0. Every solution of this system lies on this line, and every point of this line corresponds to a vector whose coordinates, vector from the origin, whose coordinates satisfy this equation. There's your homogeneous system. Now, the solution to the equation that we got, well, this vector is a solution to the equation, the vector -3, 6, 0. And that vector displaces the origin, which is on the line representing the homogeneous solution, because of course the origin's where all 3 coordinates are 0. And if all 3 coordinates are 0, well, you see what happens. Okay. If we then displace every point on this line by this vector, yeah, got to be longer than that. Of course, it has to kind of come back here. It's a little hard to do this with the perspective I have, but we just displace this and we get this. Okay. Looks like I got these 3 vectors kind of okay. This needs to be a little longer. And of course, we didn't use orange to represent this. We used red. Okay, so This is one particular solution. And this is the solution set. Meaning any vector from the origin out to this red line is a representation of a solution. The coordinates of that vector will be a solution to our original equations. So that if I sketch this vector, it's a solution. The coordinates of this vector solve the system, and the coordinates of any other vector that I wish to draw. Same for this vector. Same for this vector. Any vector from the origin out to here has coordinates that solve the original equation with the 12 and the 48 here. Now that's a big deal. You'll understand that and hopefully appreciate it as we get into the chapter on vector spaces and some of the applications. The neatest one being how you create a regression line, I think, at least the neatest one that's accessible to the level of this course. And we're going to do that, but it'll be a while yet. Okay, picture's important. Concepts here are important. And they kind of bring together everything that we've done up through the midterm exam in many ways. Oh yeah, I guess I should mention. This is the set of solutions to the homogeneous system, which is the null space of the matrix (2, 3, 4, -4, 6, -3). Okay. The row space of the matrix, in other words, the span of the vectors 2, 3, 4, -4, 6, -3. Both of these vectors are perpendicular to this line. And these two vectors span a plane that's perpendicular to this line. Okay, wherever that line is, there's a plane that's perpendicular to it. So I'm going to pause the video for a second. So I want to say just a little bit more about that. I want to figure out where to put it on the board. Okay, in the terminology that we developed just before midterm, this is the null space of this matrix. Because the null space of this matrix is the space of all vectors x1, x2, x3 that when multiplied by this matrix give you 0. Well, if you multiply the x1, x2, x3 vector by this matrix, here's what you get. So solution to the homogeneous system is the set of vectors that map to 0, 0, that are multiplied by this matrix to give you 0, 0. And that's what the null space is. You also have the row space, which is the space spanned by the vector 2, 3, 4, which kind of goes this way. The vector -4, 6, -3 kind of goes that way. And it kind of gives you a plane that goes like this. That turns out to be perpendicular to this null space. And it's easy to prove that it's perpendicular with the mechanics that we're going to develop here by the end of the month. And the proof is very simple. The calculation is very simple. You just multiply the 2, 3, 4 of the row here by the negative 3.3, negative 1, 2.4. 2 times negative 3.3 is negative 6.6. 3 times negative 1 is negative 3. Negative 6.6, negative 3 is negative 9.6. And 4 times 2.4 is plus 9.6. Multiply these 3 by these 3 and add them up, you get 0. Same thing for these 3. You can check it out yourself. If you multiply this by this, this by this, this by this, you get 0. And that proves in a way that we'll see before too much longer that these vectors are perpendicular to this vector. Something to store away. There's a lot of structure to what goes on with these transformations. Then we can say that the row space, this vector and this vector have a span that's a plane. If this vector goes this way, that vector goes that way. You add multiples of this vector to multiples of that vector, you get a plane. Now, you need a little more machinery, kind of the machinery actually developed in multivariable calculus, which nobody's had. I don't think. We don't expect you to have had it. But you're going to have to kind of accept that. And we might prove it. Anyhow, make the statement the row space spans a plane perpendicular to the null space. Okay. And that's a great big deal too. And this kind of brings us around to the idea of the row space and the null space. This vector has rank 2, but it operates in vectors in 3-dimensional space, vectors of length 3. So the nullity is 1 because you have a null space of dimension 1 spanned by this vector or this vector. And you have a row space spanned by these 2 vectors. So it all forms together into a very profound picture that allows you to do things that you wouldn't believe you could do. So there we have it.